Today we're working on equilibrium of a deformable body. We have a couple learning objectives, or at least concepts I want to mention before we get started deep into this. First of all, the objective of the course, as we know, is to relate load to deformation. We have to use geometry, we have to use material properties, and we have to use the forces system. And in order to do that, we need to look at the equilibrium of a deformable body. So far you've done rigid bodies and you have determined like the statics of the whole or equilibrium of the whole. And now we're going to start looking at deformable bodies that are not rigid. Most engineering structures are relatively stiff, all right? And because of that, we can make an assumption that they are rigid and use the equilibrium equations as if the structure were rigid. So our methods don't change very much at this point. Today I'm pretty much going to be looking at method of sections. Okay, that is what we have today. So let us get started. Okay, let's look at internal forces. Okay, we're going to make a plane. I'm going to draw a plane and a body. I'm going to put the plane in first because I think it'll look a little bit better if I do. Nope, that's not going to work. That is not how I wanted to do it. Let me try again. Okay. I love these erasable pens. All right, so okay, let me try this all over again. Okay, so this is our learning objectives today as we study the equilibrium of a deformable body. First of all, we know that the ultimate goal is to relate load to deformations. And we also know that most engineering structures are stiff. They're not all squishy. And therefore, we can use the equations of equilibrium as if the structure were rigid. So we're making assumptions, but they are useful assumptions. As we start looking at this method, we call it the method of sections. All right, so I'm going to start off looking at internal forces. Okay, to do this, I'm going to draw a body. Kind of looks like a potato maybe. All right, and this body has forces acting on it. Let's call them F1, F2, F3, and F4. So I'm drawing a free body diagram here. Now, if I take a plane and I want to section this body to expose the inside and to isolate one part of the structure so that we can look at the equilibrium of that portion. I'm going to use a plane. Let's call it plane AA. Okay, so I'm going to make some things disappear. Actually, this should have been black. Okay. Okay, so we have a body, we have a plane that's now sectioned it. Let's take a look at one side of it. I'm going to call this side of it, let's call this the A side, and let's call this the B side, just for our own notations. Those are not points. So let's look at A. Maybe it looks kind of like that. It's not going to be exactly the same, but I'm going to use your imagination. How about that? Okay, this is our cut surface on the plane AA. So if I really wanted to, I could show you that. This is section A. And we'll do a free body diagram of this. And it's the left-hand side. Now, in order to make sure that this section is also in equilibrium, just as this whole is in equilibrium, then any piece of it is also in equilibrium. We have to then determine what are the forces going on this cut section, on that plane. You know, maybe there are at every little point or every little node on this plane, you know, there is some sort of a force acting on it. Okay, and those forces are all over the surface. You know, and I'm drawing them randomly Not really sure what direction they're going in or how many there are, but I'm kind of trying to look at every point. The idea is that there's really actually a lot of them. In fact, there would be infinite number of forces if you were to look for the nodes, because there's infinite nodes. But we will use a realistic approach to this. What you want to do is we're going to look at summing up all those forces and finding one equivalent force. I'm going to just call them F sub i's. And we know that they are located at the center of gravity. Of the section. The cross section. Okay. So if our cross-sectional area is the area, and it's that area, all of these forces are internal forces. They're all acting as external forces for this free body diagram. All right, we have to maintain equilibrium. We can represent all of these forces into these resultant or equivalent forces. I'm going to call them resultant forces. R, and a resultant couple, C. Okay, they are acting at the center of gravity. I'm going to use we'll just redraw it. Anyway, they are placed at the centroid of the cross section. Ooh. I think some of my writing you weren't able to see. I apologize for that. So now, if we want to show what those resultants, couples, and forces look like, I'll just go ahead and draw the A section one more time. With my F2 and my F1. And we'll end up having, at that center of gravity, centroid, a resultant force and a resultant couple. And they act perpendicular to each other. Okay? Where this is the cut face. Now, we also know from Newton's third law it tells us that we have to have equal and opposite forces. So now if we look at the right-hand side, so the B side of it, oops, this should be black. There's the B, and in fact, I'm going to draw it slightly different. I'm going to have it facing backwards so that we can see the cut face close to us. Okay, we will have a center of gravity as well. Same spot because it's the same section. And we're going to have equal and opposite couple and resultant forces. Now, if we want to get really fancy with this, we can start to put this into a coordinate system. I'm going to use maybe blue. And we'll just go ahead and start another page. We could also redraw these on a coordinate system. With, I'll use purple. In which case, we could take the resultant force and the couple that we had here, and we could find the reflection of that resultant force onto each of the different axes planes. We will end up with normal forces and twisting forces and shear forces in every plane, or in every coordinate system direction. So we'll have a force and a moment around the x-axis. I'm going to call that N for normal. Because it's perpendicular. We're going to have a force in the y direction. I'm going to call that V. And I'm going to say sub y just because it's in the y. And we're going to have a moment about that, M sub y. And we'll do the same over here in the z. So for this global coordinate system, we know that sum of forces in the x is going to have to equal forces in the y and the z. And those will all equal 0 because we're still in static equilibrium. What this means for section A is, or for, section A, cut at the AA plane. We showed that before. That our force vector the total sum of all the forces, force vector, is 0. That means that in this case, my F1 and my F2, and whatever these are altogether, which was the resultant force, that equals 0. Well, I don't need a direction here. This is general. So my moment now these are the moments due to F1 and F2 about the center of gravity, because they are not at the center of gravity. Okay. Oh, and we have to add our couple. And that equals 0 as well. So in general, our generic response is we have to find a resultant force. Okay. Let's do some example problems. Those are more fun. Oh, I didn't get to see the summary. Okay, I'll let this go, and you should have a handout that looks a lot like this. Okay, we're going to start, and I'm going to call this example 2. It says problem 2 here. We have a problem. This is the Washington Monument. It's really tall, and it weighs a lot. Okay, in fact, it weighs 181,000 kips. It's constructed of a lot of blocks of marble and granite, and those blocks are stacked one on top of each other on a base. Now, the base is what we're looking at right now. Okay, this is the base. The inside is hollow. If we pick this thing up from the ground and look down at where the monument is pushing down on the ground, the shaded area is that contact space. It's in compression. We kind of instinctually know that. And it's due to the weight pushing down. Okay, so I'm going to make a couple notes here because it asks us to do things. We have the base, and we're supposed to determine the compressive stress. I always like circle the thing or note the thing that we have to find. The compressive stress that the foundation exerts over the cross-section. That the monument exerts over the cross-sectional foundation, or the cross-section of the foundation. There we go, of the foundation. We're going to assume that it's uniform across the whole, and we're looking at what we're going to now start calling normal stresses. And what that means is we're going to take a load and spread it out over the whole area. This is a distributed load, and it causes load per area. Often, this is my units. Let's just say pound force per, I don't know, square inch. Okay. Often we'll say that means P is force divided by area. And this is what you want. In our case, the force is the weight. Okay? If we're supposed to find the compressive stress, that's what this is in this case, we want to find this value. So we're going to say P is the compressive force, or the force, 181,700 kips over the area. The area is this entire shaded area. Lots of different ways you can go about doing that. I got 349,920 square inches, which gives us 0.52 KSI, kips per square inch. It's the same as 520 pounds per square inch, or PSI. And we call this bearing stress. Now, do you know how much that soil can hold up? This is just something interesting. I want to introduce a little concept here. This monument, if we were to draw it in a failed state, it's pressing down. Let's see. How do you know if it's going to fail? Well, you could test the soil and see what it can take. And if the Washington Monument starts, looks like a little cattywampus here, on this foundation, and we know that it's hollow, and these are 15-foot thick walls. Okay, I'm going to just do it like that. This is pushing down. So the soil, once it fails, is going to have a failure mechanism or appearance that looks a little like this. If this thing sinks down, let's just say it sinks down to here. That's going to now be the surface that you see here. So what's going to end up happening is you're going to push out some of the soil, and you're going to end up with a bulge and a depression. Maybe I over-exaggerated. I still over-exaggerated, but I think it gives you the picture, the idea. Okay, this zone, there's a zone here because this stress is being transferred into the ground, and the ground, the soil, is actually holding it, right? There is some sort of an area, volume really, over which this is being dissipated into the ground and down to bedrock. Okay, so this is your failure area. Let's say that a typical soil bearing pressure can take, I'm going to call it bearing, this is maybe conservative, but let's just say it can take 2,000 psi, right? Well, we have 520 psi. Are we anywhere near failing? No. So this is much smaller than the 2,000. Therefore, okay, from a design perspective, or at least a check perspective. But we can also do more than that. We could say how much more it is, right? In fact, we have what we call a safety factor. Because we're safe by some amount. In this case, we have the maximum bearing stress and the what we call allowable bearing stress, or the design stress. Okay, this ends up being 2,000 over 520 for a safety factor of about 4. You could put 4 times as much stress on that soil before you actually fail it. Does that feel like a good cushion? You know, for strange things that we don't know what's going to happen? And I do. That makes sense. In geotechnical work, safety factors tend to get pretty high, and so safety factor of 4 would be very reasonable. Okay, let's do another one. Okay, here's your other page. This one we're going to I'm going to call this one example 2. Please don't mind my old notation. All right. We're supposed to take this system and determine the resultant internal loadings on the cross section through point D. Right there. On this member. So we're going to be looking at this member by itself. And there is a node here that's been identified at 0.5 meter. Okay, so, well, let's draw this thing out. Let's do a free body diagram. Where's my draw? We're going to have A and B. We're going to have D as well. It's at 1/3 of the distance, so really it should be over a little bit more. Maybe here. And yeah, we could show where it's at. Now let's put our forces on it. We're going to remove the pin, and we will model it with 2 forces, AY and AX. Right? We have a coordinate system that we're going to designate our standard one. So we have those 2. We will take this pin out and we will do the same. But we're not going to have an X and a Y necessarily. We've got this tension, this 2-force member here. So we can go ahead and just draw our force, let's call it force at D. No, let's call it force at member at the point where we're going to go from B looking at C. So that's the way we'll do that. We start looking, sitting on B, looking towards C. That's the direction we're looking. I'm drawing it outward, tension, just as positive notation, and we might find that it is different than that. In addition to that, we have this distributed load. Okay, that distributed load can be modeled for this purpose of equilibrium as an equivalent load, FEQ. Okay, I'm going to just calculate up here FEQ to be 1.25 kilonewtons per meter times, it's a total of 1.5 meters. What did I get? Guess we have to take a calculator. Okay, so we have 1.25, 1.5, and I get 1.875 kilonewtons because the meters cancel out, and that's what we like to see. Okay, so this is equal to 1. Okay, and we locate it at the midpoint. So that will be at 0.75 meters. If we sum moments, I'm going to not do this all the way. Summing moments at 0, I'm going to get FBC 1.17 kilonewtons, and it's going to be in the right direction, tension. I'm going to do forces in the Y. I get AY 9375 kilonewtons. My direction is up, positive. And we will do forces in the X. We're going to get it's actually negative, going in the opposite direction. Okay. So we have finished looking at just a little bit here. We have this member in equilibrium. We know what the reaction forces are. Our job, though, is to find the internal resultant loadings at a cross-section at point D. So we're going to end up cutting the section at point D. And let's take one side or the other. It doesn't matter. We can take right or left. I tend to take left. So let's take the left-hand side. Okay, I took a moment here to draw this out. We have a free body diagram of the left-hand side. So it is member AD at this point. We sectioned it at D. Maybe this is a pipe. Okay, so maybe it's a hollow circular cross-section. We would still have AX and AY. We have our distributed load that has some sort of a FEQ. We can even calculate what that FEQ is. The 1.25 kilonewtons per meter times a half a meter is going to be 0.75 meters. No, kilonewtons. Ooh. Right. So we could cancel those out and check. Okay, that's not the only thing we need to do though, because when we cut this open, there are forces and stresses going on inside the member that will keep this in equilibrium. They're going to act like an external force. So what happens is we have a shear force that goes in the plane of the cross section. I'm going to draw it like this, pointed down as our positive notation, and call it V, where V is a shear force. When you have an open section on this side, so I took the left-hand side, the section is on the right, we will point that and use a downward. We also have a normal force. I usually call that N. Let's see what I did here. I'll just call it N. And we will have a moment. Okay, and all of these we could put, you know, a little subscript of D on them because they're all at D. So this is our normal force and our moment. So that's how we replace it's creating the effect of equilibrium for this part, acting as an external. So now we are ready to go. We can go ahead and do equilibrium. I'll pause it for you. All right, so I added a couple things here. We're going to do our equilibrium. X directions, we're going to have AX and we're going to have this normal force. We have AX plus the normal force, 0, both acting in the positive direction. As I solve for that, my AX was actually in the opposite direction, but I continued to draw it in the positive, and I have a notation here that it's negative, so we know it's going in that direction. In which case, this becomes minus 0.703 kilonewtons plus the normal force is 0. And so we end up with the normal force being 0.703 kilonewtons in that direction, right? It's in tension. Well, let's not say tension because it's not a two-force member. Well, anyway, there, we'll go with that. Let's do the next one. We're going to have a Y, which is the 0.9375. We have the FEQ, which is our 0.75 kilonewtons, down. And we have our V sub D. Okay, so if I solve, I'm going to end up with V sub D oh, I made a calculation error. Hang on for a second. Okay, so I took a moment and found my error, and it was right here, 0.625, which means this changes. So our numbers come out to be 0.3 kilonewtons down for our shear, and our moments. We can sum it about anywhere. All right. Normally, I would sum it. It doesn't really matter where we're going to do it. because no matter where we're doing it, we're going to solve, our thing is to solve for m sub d. So, well, let's go ahead and do around point D. Okay, so we're going to have m sub d in the positive direction. We don't have to take into account these two because they're right there. They have a 0 moment arm. And we're going to have a positive FEQ times the distance, which would be 0.25 meters. Okay, and that's positive because it's going to make this thing want to go in this direction, which is our positive direction. And AX is collinear, AY is going to tend to make this want to go in the negative direction. So we can do AY, or 0.9375 times the 0.5 meters equals 0. Solving all that out, I got m sub d is 0.32 kilonewton meters, and it's in this direction. Okay, whoops. Those are my values for the normal, the shear, and the moment. Normal force, shear force, and the moment at point D. Now, let's go back and I'm going to ask you a question. If I had asked you to do this problem, sectioning it right here at 0.75, could you have done that? Could you do it now? I think you can. Okay, that's all I have for you right now, and we will see you on Monday. Take care. Bye.